Thank you. Thank you, Kevin. Is the volume okay? Can you hear me up there? Okay. And I think we really have to thank the real point man and Kevin and Shelby. So let's give Kevin a great hand for all the work in putting this program together. Kevin Pitts. Oh yes, there are a few things here that you can look up if you like. But what I'm going to get on with is the main point here, which is this. So here's what I'm going to talk about today: seeing sound in solids. In fact, we're not really used to seeing sound. We're used to hearing sound or feeling sound, like a bass at a concert or something like that. You can really feel it. But you don't usually see sound. And so I think this is kind of an interesting topic. And actually, I realized that there were a lot of demonstrations that come from our demo, lecture demo prep area, and the people who put them together have a lot of neat demos for the courses and things that really relate to this topic. And why does it relate to the topic? Because I'm going to start off at a really basic level here and just talk about basic properties of waves first, because that's going to be the terminology that I'm going to use in talking about how we might be able to observe sound in a solid, in a crystal, for example. And so we're going to talk about, well, and there's really a lot of interesting surprises of sound propagating through a crystal. And we'll talk about waves that actually, you're used to maybe hearing about waves that interfere with each other. Okay? Well, in the crystal, it turns out that waves can interfere with themselves, which is kind of interesting. You have one source and you have interference pattern. So I'll talk about that. And I'll talk about heat as vibrational waves. Many of you perhaps know that sound that we hear is low frequency in the few hundreds of hertz or 1,000 hertz range. There's also ultrasound, which is just higher frequency. And ultrasound is used for imaging babies before they're born, and lots of other, looking at airplane parts to see if there's any weakness within the turbine of an airplane so it doesn't fall off and blow up the engine in flight. Ultrasound is very important, and that's in the megahertz range, which is about the range of the FM stations around here, 90 megahertz, something like that. But that's an electromagnetic wave. So we're talking about now vibrational waves here. Sound is a vibrational wave or a pressure wave. And heat also is just vibrational wave, but much higher frequency, 1,000 to 10,000 times higher than ultrasound. You're probably not used to thinking about heat as being just a very rapidly varying wave in a crystal or in a solid, but that's and it is really a vibrational wave. There's many vibrational waves, and those little vibrational waves, there's actually a quantum of vibrational waves. Quantum mechanics tells us that there's a quantum, the smallest unit of vibrational wave you can get. You can't make one any smaller. It's called a phonon. A phonon. It's like photons that you've heard about are quanta or packets of electromagnetic waves, light. And so a phonon is a packet of vibrational wave, sound. And so we'll talk about phonons at the near the end. So let's get started here. Here's some basic properties which I expect a lot of people to have seen before, but just in case. Here are two basic properties: the wavelength of a wave, and then now I'm plotting the distance, a wave. So let's take this slinky right here. And so two of the parameters there are the amplitude of the wave. So there's an amplitude associated with the wave, and that can be large or it can be small. There's also a wavelength associated with the wave, and that depends upon the frequency, of course. Here's the frequency. I'm making wavelengths that are much smaller now, or I can make wavelengths a lot larger, but I have to slow down the frequency. So there's some relationship between frequency and wavelength here. And frequency is also sometimes defined in terms of the period of the wave. The period of the wave is 1 over the frequency. Or if you have a period of a wave which is a tenth of a second, say, the frequency is 10 per second. They're inversely related to each other. Frequency is 1 over the period of the wave. And now we're plotting in terms of time here, period. But the velocity comes from those two parameters there, right there. The velocity is, well, you know, velocity is in meters per second, right? And so it makes sense that velocity is going to be a length divided by a time. And what length is it? Well, it's the wavelength divided by what time? The period. Okay? So the velocity of a wave is just whatever its wavelength is divided by the period. You can do that in terms of the frequency if you like. Okay? And in fact, notice that the velocity is wavelength over period, and we can show that, we're going to show that it's also the wavelength times the frequency. Okay? Or the frequency, I'm just changing things around from one side of the equation to the other. The frequency is the velocity divided by the wavelength. Okay? So let's do a couple of our favorite demos here to just look at some of these, set these ideas. And I'm just going to get started here with our, I think a lot of you have probably seen this nice demo. This is a rope here, actually a rubber rope, and it's being modulated up and down at the end there. And let's see, we can turn on this strobe here that will help us to see the wave. And Erica has told me the right way to turn this on. And I suppose we might want to turn the room lights out for this also. But okay, thank you, Erica, if you want to get that. And oh, and how about the screen too? Okay, so let's go to this frequency up here. And let's turn this up. Turning up the frequency here, so the period is getting less than, oh look, see we have a time just about right where you can kind of stop the wave. Actually, I don't want to do this, do I? I want to keep this at the resonance. And I want to change the strobe here. I haven't done this in a while, so this is... I think I went by it. It's a little tricky. There you go. So you can see here, I've got essentially one wavelength here, and it's going at some time. And you can also turn up the frequency, and you're going to find that the wavelength is going to change here. So let's turn up the frequency a little bit here. There were 2 half waves there, and now I shouldn't have turned that strobe on, should I? Because I can't see it so well. That's okay. It's okay. Thank you, Erica. That's great. 2 of us working together work better. So you can see here there are 3 half waves here, and that's higher frequency. And so, you know, this is kind of a neat demonstration. Let's turn the lights back on. We can do this by hand also, and maybe we can get something quantitative out of it. So we have also this spring here, and somebody want to come up and help me with this? I'm not. No. Please. You're not going to be asked to do anything really dangerous or, what's your name?
Trent.
Trent, thank you, Trent. If you'll just go stand right over here at the end of this. Now, these are 2-meter sticks here. This is a 2-meter stick, and that's a 2-meter stick. And so we have 4 meters. So I want you to kind of stand right here where you can kind of hold it at the end of that. And so we can get some waves going here. Why don't you just hold it with both hands just a second. I'll see if I can get one of those waves going there. Okay, so this is, I had a little practice beforehand. Okay, so this is, now how many wavelengths are right there? 1 wavelength. And so what is the wavelength in meters? 4 meters. Okay, so we have 4 meters in wavelength there. And what I want to do is I want to time what the frequency is. Actually, it'll be the period. And we'll have to go 1 over the period for the frequency. So, and I'm going to time 10 oscillations here, and then we'll divide by 10. Okay? And so I'm going to start the timer here. 1. You can miss by 1 here because you can't start exactly at the, let's see, clear. Okay, so here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so about 6 seconds there. And we have 6 seconds over, let's see, so let's look at our formula here. The frequency is what then? It's 1/6 of a second, right? Frequency is 1/6 of a second. Actually, that's not quite right, is it? Because that was 6 seconds for 10 oscillations, right? And so this 6 seconds here, so it's 0.6 seconds it's a little less than a second. Okay, so 0.6 seconds, and I'm looking at this formula here, this formula down here, and so we know that that is 0.6, and we know what the wavelength is, right? And what was the wavelength? The wavelength was 4 meters, so we have 0.6 seconds. If we want to get the velocity here, it's 0.6 seconds divided by 4 meters, right? I'm sorry, it's 1 over 0.6 seconds. It's the period. And it's 4 meters per 0.6 seconds. 4 meters per 0.6 seconds. And what is that? That's 4 over 0.6. That is about 6.6 meters per second, something like that. 6 meters per second. And so how would we measure the velocity here? How could we separately measure the velocity? Can you think of a way to measure the velocity? See, we didn't measure it for our standing wave there, did we? You can't think of anything? Well, yes, we can calculate it, but let's see if we can measure it, because I'm an experimentalist, actually, and I want to measure the velocity, and so I'm going to clear this. And what I'm going to do is I'm going to have a pulse rather than a standing wave. Now watch this, and the pulse is going to move at the velocity. Okay, so watch this. Okay, so what I need to do now is to time how long it takes to get back and forth. Okay, so I'm going to time it for about, let's see, how many cycles should I time it for? Maybe 10 times. Okay, I don't know if it'll 1, 2, 3, 4, 5. Okay, so let's give it a try here. And then we'll divide by 10 again here. So, and it's going to be going how far? 4 meters. So it's going to, the velocity is going to be 4 meters divided by whatever time that we get. 4 meters. Okay, so here we go. I'm going to, okay, I want 10, right? 1, 2, 3, 4, 5, 6, 7, 8. Oops. Yeah, that was a practice. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, look at that. 6. So it's 6. And so, and remember, this is 4 meters. So now I'm leaving it up to you to determine if you believe. Thank you very much. So it took 6 seconds. So it's 0.6 second essentially there. and it went for how many meters? 4 meters. And so what we have is the velocity is 4 meters divided by 0.6 seconds, which is what we calculated here from the standing wave. So we do a little bit of quantitative stuff here also. We also have some other things that are kind of interesting to show sound waves. Actually, those are waves on a rope. Sound wave. This is called a singing. I didn't know they had this, and Erica pointed it out to me, so this is the first time I've ever done this. You can make standing waves not only like from one end of the rope to the other by fixing ends of rope, but you can also put standing waves in tubes. And of course, this is how they make organs, right, is by various length tubes. And what this is going to show is the relationship between the frequency and the wavelength, okay? So when I pull the wave out, make it a little longer, is the frequency going to go up or down? Yeah, it'll go down. So let's see if that happens, okay? So it's going down. That's kind of neat, huh? Okay. Thank you for telling me about that one, Erica. That was great. Okay. There are also other kinds of, here's another wave here. This is a torsional wave here, where we have a wire, and these rods are connected to the wire. And the torsion, it says it gives a restoring force. And so this is kind of a neat one. You can make little waves. There's a pulse right there. This is just illuminated by ultraviolet wave. Okay, so here the pulse is going across there, and it reflects back. And you can make a wave train, okay, or you can make just a continuous wave. Here's a continuous wave. It's going to reflect off the back there, so then you'll have interference coming back there. But so there's a continuous wave. We're going to be talking about really continuous waves and pulses. When we talk about, when I show you these experiments we have on sound traveling through crystals, we'll do a pulse like that, or we'll do a continuous wave. Okay? So let's see, what other, if we get to about halfway through this lecture and you see that I haven't done something, will you raise your hand and point to it and say, what did you forget over there, okay? But I see here we also have something that shows ultrasound. But it isn't really ultrasound. It is going to be sound. We have a glass here, and we've got a loudspeaker. This doesn't look like your loudspeaker because it just is the element for the loudspeaker. And so we're going to turn on some sound here. And did everybody bring their... no? Oh, okay. You might want to, if you're in the first 7 rows, I think maybe you should. I haven't done this before, so I don't... Can you hear me back there? I can't hear you. Okay, so let's see. So, power on, and I think it's... Oh. Okay, Erica. So what do you think, Erica, about that? About like that? Up more. This glass resonates at a certain frequency, and we're going to try and hit the frequency. This is, you can see it on the screen up there too if you don't. Okay, so I think maybe I need to adjust the frequency a little bit. I don't know if we can stand this. Okay, what are we going to do, Erica? See, because I don't have a thing to hold my ear. It's worse up here. Okay, we're gonna save this till the end and allow those of you who still have ears that work to remain. Okay, and we'll try it again at the end. Okay. anyway, most of the stuff that we do is not destructive, so actually that's probably good it didn't work, right? Okay, so basic properties of waves, okay? There are other waveforms, and this is what I already mentioned to you, is there are the harmonic waves, the sines and cosines, but there's also pulses and wave trains also, just a few waves. So for a given medium, it turns out, and now this is maybe a surprising thing, which of these waves do you think would travel the fastest? Well, actually, they all travel at the same speed because it only depends, the velocity only depends upon the density and the elasticity of the medium. So no matter what, I mean, we used that principle to get what the velocity was out there, that it doesn't make any difference whether it's a pulse or a harmonic wave, it travels at the same speed. And so another demonstration of a pulse is this neat little drum here that Bernie made. And I get to try this for the first time, too. This looks like fun. You see what we're going to do here? We're going to put some exotic gas in there, right? And actually, it's going to be air. And what we're going to do is we're going to pump this thing like this. Anybody feel this? Got it? Nobody? Got it? Did you get it? Raise your hand if you feel it, okay? Let's see, here we go. Okay, that's going pretty far, actually. If we can make her little hair stand up. Well, wait, there's another way we can do this. If somebody would help me here just for a second. If you just hold this up, we'll be able to see it. Hopefully see the wave. So there's a pulse that I'm generating here. It's a vortex pulse. It's actually much slower than the speed of sound. If you stand right over there, so everybody can, or maybe over there. And, oh, you can't go any further. Okay. So let's see here. Just to prove, those of you who didn't feel it. Now, are you moving it? No. Really? Okay, put your hands behind your back so we know that that's the case. Okay? Okay, anyway, you got the idea there. So that's a pulse. Thank you very much. Oh, there is something else we can do here. Oh, yeah. Okay. Let's see here. I've never done this before, so this could be very dangerous. And, oh, yes. This is actually a hot air balloon. Okay, Erica, you can let me try this myself, huh? No? Not high enough.
I'll give you a hand, but you can...
Okay. Oh, okay. Oh, that's great. So I thought that rather than just have, I mean, you did a great job. You did a great job. But rather than just having somebody hold it, I think we ought to see if I can make it move, right? Wait a minute, got to get aimed here. Come on. Anyway. Thank you, Erica. Oh! I'm glad you didn't wait till the end there, Kevin. Now, how far can I stand? Can I stand this far away? You think so? Can I stand this far away? This far? Can I? Will it reflect off the wall? Did it go out? No. Okay. Oh. Ah! I'm going over it. Okay. No help here. Don't blow it out. Oh, yes. Now, nobody saw Erica blow that out, right? No. Okay. Thank you. That was a great idea. Okay, wave rope probably, we have neat programs, and I'll just show you some programs that we have at the university here where we can do things like this. And we see that that wave will, oh, it's a free end. So let's change the boundary conditions here. We're going to make there a fixed end here. And so now let's see what happens to this wave. What do you think is going to happen? It's going to bounce back, but anything else? Bingo. Isn't that neat? A reflected wave bounces back inversely. Do you want to do it again? Wave pulse. Hey, we're going to get some interference now. Whoa. We almost got a standing wave there, didn't we? Let's see if I can do this. Okay, so I'm going to try and do it. We may have to come back next week to finish up the lecture, okay? Is that okay? I'm trying to do this equally here, because I want to see if I can make a standing wave. So you're going to have to tell me if I succeed here. Oh yeah, look at it. It's kind of a standing wave there, because it's moving in the opposite direction. Whoops. Anyway, you get the idea. You can play with this all day, actually, and just have some fun. There are different kinds of waves you can put in. And okay. So there's also a phenomenon, what I was just getting to here is superposition of waves, the fact that waves add to each other. The wave going over there reflected back to the other wave, and they interacted with each other. What was the principle for that? Well, if you look at any one point on the rope, it adds up with the appropriate sign whatever the wave is, the two waves are. So if there's one positive and another negative, then it'll go to 0. If they're both positive, it'll double the amplitude. And so we have some movies like this too. So let's see what happens here. So here's two waves coming together. And look at when they get, this is the sum down here. Okay, in case you didn't catch that, we'll do it again here. So I can stop it so everybody see what's happening here. We're summing up the two waves. This is called superposition. Notice that if I take that blue one and the green one there and I add them up, I'll get something about this high. Right? Superposition. There it is, right there. And here, you see now the center there is about twice this height. And if I go on, and I stop it, whoops, I meant to stop it there. It was twice the height there. But you know, there's an interesting thing you can do. What if you make one of the waves negative? And of course, we have that too. And so, what's going to happen here? They're going to cancel each other out, huh? Okay, well, let's see. Is it starting to happen? See, this is negative here, and that's positive. And so negative plus positive gives something less. And here we go. Oh, look, what's going to happen next? What do you think? You think it's going to disappear? How many say it's going to disappear totally? Well, not forever. I mean, disappear totally for an instant. Okay. How many say it's going to disappear totally forever? Oh, okay. I was going to ask you to leave. Okay. No, you really need this lecture. Okay. Anyway, here we go. You got to watch closely now. Boing. So it did go away, didn't it? I'm going to try this again. And I'm going to try and stop it in the middle, okay? I'm never really able to do this quite right. Ah! I think it's time to retire. Now, let me ask you a question here for you people who really want to think about things. Here we've taken a snapshot of this rope. And we know that it took energy to make the rope move. The person on the right side took energy, arm energy, the cereal ate in the morning, went into chemical energy, and you know. Anyway, and that took energy. And the person on the other side who went like this, down, did he or she have to use energy to do that? Or negative energy? Negative energy? Well, negative energy would mean that the rope gave U energy. Right. So it's a negative amplitude, but energy is actually the square of amplitude. It's the square of amplitude, and so any negative amplitude gives a positive energy. Okay? So there was energy there and energy there, and if it was the same height of wave, we've got twice the energy going in, and now we're looking at the red line here. Where did the energy go? Energy is conserved, isn't it? In an experiment where you don't take things out, the energy was in the rope 1 minute, and now where is the energy? Anybody want to tell their parents, if their parents are here, where that energy went? Because in a minute, if you don't, I'm going to ask the parents. Okay. Any parent want to tell me where you think the energy is? This is a great puzzle, isn't it? Energy is conserved. Anybody? Heat. That would be dissipative. And so you can't get it back then, because this is, yeah, it would heat up the rope and the rope wouldn't suddenly cool down and give it back. Potential energy, no, it's not really. It's not like a spring, really. It's not quite the same. Yes? Yes? Is it right in the middle? Well, that would have to, okay. I'm going to tell you the answer here, okay? The answer is that the rope, you don't see it, but the rope is moving. And what is kinetic energy? Kinetic energy is motion. And so the fact that the rope is moving very fast, in fact, it's moving its fastest right here because it's going like this. It's starting out like this. And so the rope is moving very fast there. I'm going to let it go, and you'll see that if I now start it up again, you'll see the rope is moving very fast, and that's kinetic energy. So the energy sort of went like from potential to kinetic energy. That's right. Okay, so here we go. See, it was moving, the rope was moving very fast there. So energy is conserved throughout that process. That's kind of neat, isn't it? How many of you have heard of energy conservation? Okay, so now you have a new take on it, right? So what about waves in 2 dimensions? Let's look at this. I got another puzzle for you here. This puzzle might be a little, well, I don't know if it's easier or harder. Let's see what happens. There's something wrong with this picture. This guy is dropping some square bricks into the water. And what's odd about this? Square waves, right? Now you expect they'll be square sort of nearby, right? But you don't expect them to be square way out there, do you? It shouldn't depend upon the size of the rock or the shape of the rock you drop. After a while, water waves just get circular, right? Well, this phenomenon is something that Mr. Huygens in 1678 put down on paper, and he said, here's how you explain this. He didn't have this cartoon, but he did it more in general terms. Consider each point on a wave front. So here's a wave front here. And you consider that each point emits a circular wavelet. I'm going to use the word wavelet a lot here. Because a wavelet is what I say if you drop a pebble in a pond, that's what comes out. It's from a point source. Drop a pebble in a pond and you get a wavelet. Drop a brick in a pond and it's not really a wavelet. You get something square at first. But the wavelets are still important, even for the brick, because at every instant, the crest there has another wavelet, can be viewed as having a wavelet coming from it. That's called Huygens' principle. And you can see here's a previous wavefront, and now we draw a bunch of little wavelets, circular wavelets, and you get the next one. And you see what happens with the brick here? If I drew a lot of wavelets from the surface of the brick, it starts to round out. And then I draw wavelets from this, and it rounds out more and rounds out more. Eventually, it becomes a round wave. Okay? Am I finished now? No. How much time do I have? Another 3 hours? Yeah. Okay. Got the room till 5. Okay. Are we catering lunch in? Okay. So the wavelengths, anybody have any questions about this? You know, if you have questions or you want to say something, yes?
If there are infinite number of points, then the wavefronts are infinitely small, are they not? So why wouldn't they still stay square if there's an infinite number?
No, because there's this distance here is determined by the time, because that's the velocity of the wave. So at an infinitely small point, okay, then it's going to travel out perpendicular at whatever the velocity is, okay, and then you can make another point just next to it, okay, and it will travel out, and so those will give rise to, you know, if you drew many more of these, it would be almost exactly like this. That would be the end points of all of them, and what happens in the middle is they cancel each other out. They cancel each other out here because you've got plus and minuses coming, and so you end up with just another wavefront. Did that sort of answer the... What you're worried... Yes, it's the radius is determined by the velocity. The radius doesn't get smaller and smaller with a wavelet. The distance between wavelets can become as small as you want. The distance from the point sources. Okay, so let's solve a problem of really great importance. This is called two-slit interference, but I shouldn't have said that because I've taken it out of the slides here. And we call this interference of waves. If you have two waves, let's say a water wave, here's a problem that you might relate to. A water wave hits a barrier. Let's say this barrier was constructed to protect homes on the shoreline. See, I can talk about this problem here. I wouldn't bring this up on the coast, but or in the Caribbean. And so the water waves come in here and they hit these two openings because boats have to go through. But what's going to happen here? What's going to happen to this opening? What is the wave going to look like over here? Right, it's like a point source, you see. And so what's going to happen is that you're going to get these wavelets coming out here, one from each of these. There's circular wavelets that are produced at each opening. And so these wavelets are going to interfere with each other depending upon where you look on the shoreline. And in some places, the wavelets might interfere constructively, add up to a bigger wave, twice as big. In other places, they might collapse to nothing because they cancel each other out, plus and minus, right? And so the question is, what's going to happen to these houses if a tsunami comes by here and hits this? And so what is the resulting wave amplitude? And we can plot this up. And this is a problem we do in one of our physics courses. And it looks something like this. This is sort of the intensity of the wave. The intensity is the square of the amplitude. Okay, it's the energy in the wave. Okay, and it looks like this. And you know where these maximums are, that's constructive interference, destructive interference. Where the maximums are depends upon the wavelength and the distance between the two openings there. And so we can see here what's going to happen to this house here, and this house, and this house. Well, this one is going to get creamed because there's a large amplitude hitting the shoreline right there. This one, there's very little amplitude right here. And this one's sort of in the middle, so they might just have to clean up their yard or something like that. But there's an experiment we can do to show this, and it's called our water wave experiment. And I'm going to start it up. Oh, here it is. Okay, thank you. And, okay. And I can turn it on. Oh, here. Great. Great. Well, this is neat. So, I can change actually the frequency here. And does everybody see the constructive and the destructive? You see those lines where there's no waves coming in? There are several lines there. And that's where it's totally destructive interference there. If I change the frequency, this is really kind of neat. Higher frequency, the lines get closer and closer together. Low frequency, the lines are farther and farther apart, the lines of destructive interference. Do you see? Okay. So we can do that, but we can... This talk is really, we're going to leave it on just for a minute, Erica. I'm just going to leave it on for a minute. going to pull up a program that we have here, which if we take a couple, let's see here, slits, number of slits. We're going to make 2 slits here. Yes, please. Okay. Can't do everything at once yet. Okay. What happens is this program will show you if you wanted to quantitatively understand this, you have vectors, and it turns out that you can plot up what the intensity is as you go along here. And so if you want to know more about how to get this, we can make this program available to you. And so it's also in our physics courses, because our engineering physics courses. So, okay. And so we also have handouts here. So let us, maybe you guys could do one. And actually, if you pass them along and take just one, I'm going to start up at the top here. Okay. Okay. They need one of each. They need one of the white paper and one of the Mylar sheets. And this is for you to take home, and you're going to be able to see when you put these together. So that's one of them, and that's the other. They're the same. And so if we start the sources off right here, then it looks like just one of them. But if you start the sources off like this, you get these patterns, which are the interference patterns, right? So you're going to see the interference patterns. So you just put them together. You need a white one and a Mylar one. You need a white one and a Mylar one, and you'll be able to do that. Plastic and paper. And you can raise your hand if you have one or the other. Oh, you got 2. He has 2 plastics. Does somebody have 2 papers? There you go, right behind you. I'll let you guys work on that. That's not my problem. Okay, so let's consider waves in crystals now. Okay, now that we know all about waves. And what kind of crystals do we study? Well, we study crystals like silicon. Here we go. Silicon has this kind of crystal structure. These are the atoms of silicon. It's really kind of complicated looking, but it's actually a cubic crystal. Here is graphite. This is carbon, different crystal structure. Anybody get 2 types of atoms? Sodium chloride. Salt, okay, is like that, okay? Salt crystals. And so there are all sorts of crystal structures, and we slice them into little squares, and we put sound waves on one side and look at the sound waves on the opposite side, okay? And so there are 2 types of waves in a crystal, and one of them is, that you haven't really seen so far, is, well, remember that we call this a transverse wave. Like that. That's a transverse wave. I can just do this and make a wave. That's transverse. Transverse to the direction. Okay? There's also a longitudinal wave, which is a compression wave. Now watch carefully. See that one? Compression wave. That's a compression wave versus a transverse wave. Okay? And those are different kinds of waves that are, it's important to, because which of those waves do you think travels the fastest? The compression wave, because it's really pushing on the next stage there. So the longitudinal waves are much faster than the transverse wave. And here's a program that we have here where we can add a few atoms here, and we can have initial conditions, normal modes. So there are many normal modes for this. So let's go here. Oh, it's really going fast there. And options, speed adjustment. There we go. Here's another normal mode. Look at it, it's faster, twice as fast, almost. Faster. Each crystals are composed of atoms with bonds between them. And so you can imagine the atoms vibrating against each other. And this is a normal mode, essentially, for one of those. But there are a lot of frequencies involved here. So let us stop and let's add atoms here. So here's like our crystal with the bonds, and so now we're going to go. I have to choose. Here is the lowest frequency vibration. This would be ultrasound, or actually, it's still pretty high frequency. It's still going to be in the megahertz. You can see it vibrating there. Or here's a middle one here. Okay? Or here's the highest frequency that you could excite, where the two atoms are right close to each other. And that's a very high frequency wave. So there are a lot of these kind of waves in the crystal, or possible waves. And so let us see, how do we image waves in a crystal? How do we see waves? This is what I was setting this whole talk about. And here's what we do. We have a device which is called an ultrasonic transducer. This right here is a sonic transducer. It takes electrical signals and it makes them into unbearable sound. But ultrasonic means that it's higher frequency, megahertz. And how do we focus this? Well, what we do is we have an ultrasonic lens. And what is that? I have one of these here. It looks like this. This is an ultrasonic transducer. And it has a little concave area here. You can't really see it, unfortunately, from where you are, but I'd rather not hand these out. Right in here, there's kind of a concave area. And so you start off a wave on this side, and it goes through the material, and then it comes to this area, but it has to be in a medium, and the medium is water. So watch what happens here. What happens is you get a focused sound wave from one of these, okay? And in this water bath. And so let's see what happens next. Next, the lens focuses the ultrasound onto the crystal. So here's our crystal. But we need to detect the sound reaching the other side of the crystal, right? And so what are we going to do to detect the sound on the other side of the crystal? Anybody want to guess? I got two of them, okay? So it produces a sound, and the other picks up the sound, it goes to an amplifier, and we detect the sound, okay? And so there it is, and here's a blow-up of it. So here is a radio frequency generator which produces this sound wave, this ultrasound. It hits one side of the crystal. Then there are waves going to be going through the crystal, and we are going to be able to pick up the wave at a given point on the other side of the crystal. But that's not an image, right? That's just point to point. So how do we image this? Well, we could take a lot of points, right? And in fact, that's what we do. We scan this receiver up and down like this. Whoops. We scan it back and forth like this. Okay? And we measure what the intensity is all along this surface. So we're scanning this back and forth, and we're going to see what the wave looks like when it reaches this surface. And are you ready to see what it looks like? Let's see here. So I have an image. This is an ultrasound image, and watch what happens here. Now, this is real data, and it actually takes about a microsecond, 1/1,000,000th of a second, for the sound to get to one. That's from the velocity of sound in the medium, from one side of the crystal to the other. So this imaging has to be very fast, right? It's not done with a regular camera. But let's look at this again. I played this. I want you to see. What do you see here? What's that? Hey, there's something else here. What do you think those two features are there? There's sort of a fast feature and a slow feature. One that arrives quickly. It arrives quickly. There it is. And it's sort of spherical. It's like a wavelet. And another which arrives much later, and it's very oddly shaped. Exactly. Compression and shear waves. So this is the compression wave, and it goes out more or less circular. And now we've got a shear wave, which can have a polarization in different directions. And it's slower, and it has a much different shape. It's kind of neat, huh? We were the first ones to do this sort of experiment here a few years back. Matt Hauser was a graduate student. So here's snapshots of that at higher frequency with more resolution. And so these are 3 different times. And you can see these waves. These are the transverse waves. And they have this sort of really interesting, that wavelet is not circular. It's not like waves in a pond. It's very different. I would ask if anybody can explain to me why that's true, but it took this student quite a long time to figure this out. Here's a close-up view of the ultrasound pulse in a silicon crystal, and you can see it has this really interesting structure. That is a single wavelet. Imagine dropping a pebble in a pond and seeing something like that. You would never see that. Okay? So how can we understand these non-circular wavelets? Well, there are other experiments that we can do, and one of them actually was done much before us, and quite a ways, a few decades ago. But I'm going to ask you a question first. Let's say instead of a point source, we have a plane source, and we put this ultrasonic plane on the crystal, and we ask, what is going to happen? Are the wave crests going to go like picture 1 or picture 2? How many say picture? How many say, okay, picture 1? Okay. What's your name? Okay, no, never mind. Picture 2. And how many say they have no idea and it's almost lunchtime? Okay. Okay. Well, actually, here is what I call a very surprising result. This is the experiment that was done by Stout and Cook in 1967. And it shows that the wave in this quartz crystal goes off in a direction which is not normal to the wavefronts. Okay? That's really interesting. It's sort of like, okay, I've drawn a picture of it over here. The energy flow is not in the same direction as what we call the wave vector is normal to the fronts there. That's right. It's not. And in part because, well, let's see. I'm going to try and explain this. I've never, well, first we'll say the Wizard of Iz. For my next trick, I'll move this pedestal without touching it from point A to point B. There's point A, and there's point B. Okay, well, he doesn't know about this stuff. But anyway, the king is over there looking like, okay, he's never much impressed with the wizard. Kazam! The wizard does it. Oh, and the pedestal screeches to a halt there. What is the king going to say to this? What do you think? Is he going to say, wow, you just blew my mind. You had those powers. What is the king going to say? Big deal. How do I know that's point B? Okay. Anyway, energy does not travel normal to the wave crest is the point I want to make here. And that's a common property of all solids. And so let's, here's a little explanation of it. It says that because a solid has planes like this, the sound is going to travel a little different velocity along one direction versus another direction. And so if we plot up what the wave crest would be for that, it would look something like this, where the velocity along where the atoms are closely spaced together, it's going to be stiffer. And so velocity is going to be higher. So this is what a wavelet would look like for this crystal, say. And if we put a bunch of these wavelets together on a line, then look what happens. It makes these crests go off in an odd direction. So that's the explanation. I thought of that last night, putting this together, and hopefully you get a little bit of the concept of that, because it's such a really neat experiment. And okay, so how do we explain the wavefront image in silicon? Well, it turns out the wavelets in silicon look this, and I'm not going to explain to you why it has this feature right here, but that takes a little more time. Here's the transverse wave, and here's the longitudinal wave. And so we can see now, this is the movie you've already seen, there's the longitudinal wave, and there is the transverse wave. So the wavelets are not circular, and we can understand exactly why that's true based on the crystal structure. And so another thing that's interesting is a continuous wave. Now that was just a pulse, right? That was a pulse. A continuous wave, it interferes with itself, because the wave that arrived, let's say, Here's a pulse source and a continuous source. This part, this wave, right, these are all in the same direction. Now, if I superpose a lot of waves that look like this but are spaced a little farther apart, they are going to interact. This part's going to interact with that part of the next wave, and there's going to be interference pattern. And this is what that interference pattern comes from. And this is the concept that I mentioned before, is the wave can interfere with itself. There's only one point source here, and yet it interferes with itself. And this is really a fantastic result here. And if you change the frequency, look what happens. The waves, the interference peaks. As the frequency goes up, the wavelength goes down, and the interference peaks get closer and closer together. We call these fringes. Well, what happens at really high frequency? Because look, they're getting very close together here, these fringes. And what happens is, high frequency, as I mentioned before, is phonons, which are the source of heat in crystals. And so what we need to do is we need to concentrate some phonons here, and we need to image them on the other side of the crystal. So like photons, phonons are packets of heat as opposed to electromagnetic energy. So here's some just phonons lolling around. And now we cool the sample way down, and we put a laser on one side of the sample. And we create a lot of phonons here where they weren't before. And then we're going to detect the heat with a little, it's called a bolometer. It's a superconductor. It's a very, very sensitive heat detector. And this crystal is at 2 degrees Kelvin. Not this one, but the one I'll show you. And here's the heated spot. And so what's going to happen is now we can't move this detector because it's deposited on the sample. So how are we going to image? Anybody have an idea how we're going to be able to image? Exactly. Why not move the source? And so, very good. So we move the source here like this. So we can scan the source like that. That's the same as scanning the detector, right? Okay. And watch what we get here. This is a crystal of germanium, and you can see these fantastic patterns of heat propagating across this crystal at 2 degrees Kelvin. And these lines here are where the interference points were kind of converging, and they're called caustics. And they're caustics in the sense that a lens produces heat also. And so the analog of the phonon optics is like sunlight hitting a swimming pool. Sunlight comes with the beams all in one direction, but refraction takes these beams into different directions. But if you look at each of these beams, you find that where there's a flat in the surface, then there is a large amount of energy going in certain directions. Okay? And that gives a caustic at the bottom of the swimming pool. Have you ever wondered about why there are those caustics at the bottom of the swimming pool? Those bright lines that look something like this right here. This is a reflection off some. So here, those are, I can't hold it very still here, but you can see, can everybody sort of see what's happening here? There are very bright lines there, and those lines are just like what happens on the bottom of a swimming pool. I'm not going to get to that one. So let's time resolve the phonons, the heat pulse, and here's what it's going to look like. It's a little different, much higher frequency. There's a longitudinal. Whoa, transverse. Look at that. It's an intercontinental ballistic phonon there is what I would call it. Let's try this again. So those are the transverse waves coming across. Longitudinal, transverse. And this is all done at 2 degrees. It looks much hotter, but it's really at 2 degrees Kelvin. So we can compare and look at, you can see the similarities between 50 megahertz and 100 gigahertz. 4 orders of magnitude higher frequencies. And these are the collaborators that I had for this experiment. Now, if there's something you see up here that I haven't done that you want to see, I'm not going to do the glass, okay? It's too painful. Yeah, it's too painful. And so, you want to hear the glass go? Okay. We'll let people who want to leave can leave, but we can try it again. We'll try it. But that's all. I'll answer any questions. And the tape. The tape. The laser's here. Yeah, I said that I wasn't going to. I think that I'm beyond that one, but I wasn't sure I was going to get to that one. And I blow out the candle. Oh, we'll do this one. Sure, this is easy. Ultrasound in water. Thank you. You've got to have helpers to do these experiments, see? And so this is, this is the sort of thing. Did you get this from a doctor? Is that that's the one that you, like this? Yeah, okay. Here we go. Ultrasound, or well, it's sound. Whoa! That's what happens with my Sonicare toothbrush also. In fact, I didn't know about that till they advertised it that way. See, if you get your teeth close to it, it cleans them much better. You want to borrow? I wouldn't put this in my mouth, but you know what I'm talking about. Okay. Ultrasound in waves. Thank you very much. Erica's tried, right? Okay, that's okay, Erica. We put a little thing up here. We can probably get it close, right? Okay, okay. If there are questions, yeah, we'll do this. We'll do this. Any other questions? Okay. Yeah, Inga. To interfere. Yes. Yes, yes. They are different polarizations, and this is like the slinky. If you notice how long it takes for a transverse wave to get across there. Here we go. Bang. Okay, let's see. Okay, now we'll do a longitudinal wave, longitudinal polarization. Here we go. It dissipates. It's actually not that much different for the slinky. You know why? It's because the slinky is made up of transfers. But the compressional waves are faster because they're changing the volume locally of the crystal. A transverse is a shear wave. It doesn't change the volume. So there's not as much restoring force. Thank you all for coming today. It was really cold out there. Yes?
If you have crystals were similar to graphite,
Yes.
where everything is square, that is, yeah, everything's square, then you wouldn't get this pattern going off and an edge that comes straight across?
Actually, you're right. If you put the wave, so here's a nice square one here, okay? If you put the wave in this direction, okay, its energy will flow in that direction. But if you make the wave go in a direction a little bit oblique from that, okay, then there's a different velocity there because you're trying to set up wave crests along a direction. And so there the energy tends to kind of want to go back in this direction. Instead of, so if you excite it like this, the wave fronts go like this, but the energy goes like that. And so you will get this funny behavior with the oblique wave.
When you put the bonds at 45 degrees then,
Yes?
what happens then?
Each crystal has its own caustic pattern depending upon its symmetry. And all crystals have caustic patterns. And so you can't make one that doesn't. So what would not have a caustic pattern would be a continuous solid, okay, which didn't have atoms or specific directions, preferred directions in it. And so if you take, say, fused quartz, which is not crystalline, it would not have that behavior. Amorphous quartz would not have that behavior.
Okay, let's try the glass, and then for any of you who might have any additional questions for Jim, I'm sure he'd be willing to talk afterwards.
Sure. Okay, I'm going to try it here. What Erica tells me is, let's put the overlay on so we can see. It's on, okay. It says you can adjust the frequency by looking at this little piece of paper that we have here. Well, I have to try this. I'm an experiment. No, you stay right there, because if I fall over, or where did my protection go? Okay. Erica, put your protection on. A hand for Erica and Caitlin and Marion. And is Bernie here? See, if it were just me, I'd come in and give you some boring slides, but this is much better, right? Okay, so we can take it kind of low. Oh, it's moving. So look, I think we're in good shape here. I don't think we quite have it. I think that this is a special diamond glass. And it, yeah, you're probably not focused right onto it, right? Bernie changed the focus on this. You had it, and Bernie changed it. He must have wanted us to fool around with it. Okay. This has worked in the past.
Yeah.
And our insurance is paid up, right? Okay. There you go, getting close. Go ahead, put it on up. It's unhappy. Good try.